Good afternoon, class. In today's video, what I'd like to do is talk about the second law of thermodynamics. This one, and like I said in the previous video on the laws of thermodynamics, this one deserves its own video all on its own, so here we go. The second law of thermodynamics says that the entropy of a system, the change in entropy, will be due to the heat, is proportional to the amount of heat that is transferred in or out of the system divided by a constant temperature. So at a constant temperature, the amount of heat that's transferred between the system and the environment will determine how much the entropy will change. So, of course, those are three words that we do definitely need to define, because otherwise there's going to be a lot of misunderstandings, especially when it comes to entropy. So what I thought I'd do is I'd throw out a few of the definitions that I've heard, even read in certain textbooks, but I thought I'd give you the one that I like the best, and that will usually be the last one on the list. So here we go. When we talk about entropy, a lot of times you'll hear, especially in popular media, is that it's the amount of disorder a system has, or it's a measure of randomness in a system. And those work. They're not terrible definitions, but they don't cover a whole lot. Like they don't keep up with the idea that the system has many ways of gaining energy, and of course this randomness makes it sound like the whole system is like conscious or something like that. There's some kind of consciousness involved, and so that none of that is actually in there. But you get that sense from these two definitions. And also, what is disorder? Does it mean, because, like, for example, is water disorder because it moves about and it just flows? So it makes it sound like only solid things are ordered and have low entropy, where you could have water sitting in a bowl and that's very ordered, even though the water can move around quite a bit. So that's why I like to take the third definition over here, where it talks about entropy being the number of energy states a system can be in. This one to me works better, because then it doesn't include just the idea of simply how a system can move, but it also gives you an idea of an ability to predict something. So for example, if you built a sandcastle, you could say, okay, well, how many ways can you build a sandcastle and it will be a sandcastle? And the answer is one, pretty much. There's pretty much only one way to build a sandcastle for it to be called a sandcastle, especially once you've shaped it, right? However, if I took a pile of sand and I said, how many ways can I make this thing a pile of sand? The answer is quite a few. So if I knock over a sandcastle, what I've done is I've increased the entropy. I've increased the number of states that it could be in. Because even if you said, is the sandcastle disordered now? Yes, technically it is. It is technically disordered because it's now just a pile of sand. Is it random? Yes, technically it is random because you don't know where all of the particles are. However, those particles are still in a certain place, which is that pile of sand. So even these definitions don't really have a good solid grasp of what is going on when it comes to entropy, because entropy just states you want to have more energy states. The system needs to be able to be freer and move in different ways. And so because of that, it would be easier. That's why I like this third definition better, because when the entropy of the system goes up, that means that there are more places that and there are more ways for that system to move. So, for example, even in your life, the entropy of your life is actually going up, especially as high school students, because within the next few years, and for some of you next year, you will be going to college, or you'll have at least three major choices to make in your life: college, vocational school, or the military. So those are three major branches that will have insane levels of consequences for your life. And all of that will be made right now, versus your life so far has been pretty well ordered. What have you been doing every day since you were about since you were in at least kindergarten or first grade, you've been going to school. That has been your path in life this entire time. And the reason for that is because it's the law. You have to do this, at least here in America. Other countries may have different standards, but for here in America, yeah, you've been going to school. You've had one path to travel your entire life. But now you're going to have a choice. You're going to have at least 3 choices, major choices. And that's not including what you do once you either go to college, go get a job, or join the military. Because like even with the military, there are branches of the military that you have to join, and those are other decisions you have to make. So that's really what entropy is. The entropy of your life is going up, and that's actually a positive thing because you're getting more choices, you're getting more freedom, but with that freedom comes consequences and also responsibility. So that's why it gives, because most people think of entropy as just this bad thing, but it can be a really positive thing, especially as you are maturing and becoming more and more of an adult. So that's what I wanted to go over, because this concept is very much, it's one of those ones where it's hard to understand unless you have, a really good picture, and even the pictures that people give are not always that great. So let's go into heat, because this is another one. Most people have they talk about heat, but then everyone starts talking about about certain concepts that don't make sense. For example, some people say you can store heat. This is completely false. Even though, based on certain definitions that people have heard, that's not unreasonable to conclude. So this is the one that most people will have heard in high school textbooks or in several textbooks, but that heat is the energy transferred from one system to another due to a temperature difference. So if somebody says, oh, could you store heat? This definition is not really good about helping you figure out whether or not the heat can be stored. It's kind of ambiguous in this. But I feel like the second definition is a lot better, because then it makes it very clear about what's going on. So heat is the energy transferred due to non-mechanical and non-electrodynamic sources. So anything that makes the heat, anything that makes energy flow between two systems would, and these of course are non-mechanical, non-electrodynamic. So you can't, it's not like plugging in something into the outlet. It's not like lifting something higher. If it's due to something besides that, that would be considered heat. And it's a transfer of energy. It's not something that you can store. So it has to there's always this interaction between other sources and the system that you're looking at. So that's why I like this second definition of heat a little bit better. And of course, if you're looking to see these definitions and write them down, please feel free at any time to pause this video so that you can look at them and zoom in as much as you need. Now let's go on to temperature, because in this one, I have been talking about temperature, especially in this heat definition. I've talked about temperature, but I haven't really defined it. And so this is where I go for it, and I'll let you know at the beginning that temperature is not something that, I wish I could easily calculate it for you. I could give you I could write a formula on the board and you'd say, there's temperature, and now I've got it. Unfortunately, that's not how thermodynamics really works. Because we're talking about group behavior instead of individual behavior, it's much harder to pin down an equation that deals with what's going on, in these concepts. So here we go. Temperature, the thing that really is this whole second law is based off of, goes like this. It is the average kinetic energy of all particles in a system. At least we know what a system is, but you've got the average kinetic energy. Well, how do you measure that? It's very hard. You can't do it using all of the other equations that we've dealt with in physics, like kinetic energy is 1/2 mv squared. That doesn't really apply because we're not talking about one particle anymore. It's all particles in the system. So, and to measure all of those, how should I say this? And to measure all of those particles and all of the kinetic energies of them all, that's it borders on impossible. It may not be completely impossible, but we certainly don't have the technology to monitor the kinetic energy of every single particle in a system, especially for things that have trillions upon trillions of atoms in the system. I mean, even just take this whiteboard for example. This has trillions upon trillions of atoms, and somehow I can figure out what the temperature of this is by just taking a thermometer and just touching it to this, and I could figure it out. So that's why temperature it has a more vague definition, and I apologize for that, but that is the way it goes, especially when it comes to talking about groups and systems. So that concludes the video on the second law of thermodynamics. Good luck in your studies, and may the force be with you.